Hi everybody. Welcome to Lecture 13, where we're going to discuss simple models of neurons. This lecture is going to be broken up into two videos, the first one giving background theory and then the second one discussing particular neuron models. To date, we have looked at networks of neurons and systems in the brain. Studying the brain has informed neural network design, like how the visual cortex has inspired convolutional neural networks. But we haven't yet paid much attention to the neurons that make up these networks. Over the course of the next couple of lectures, we are going to develop models of neurons of increasing biological fidelity. And we're going to start with basic input-output models of neurons, then add greater internal detail, and finally we will explicitly model the biophysics to explain observed neuron behavior. These models of neurons that can replicate or explain observations from biological experiments. And the purpose for studying the constituent cells of these networks is so that we can, A, better understand the biology, and then we can perhaps learn something about how brains behave by understanding the units that make them up, and B, we can use them to make new and better neural networks, like the development of neuromorphic computers. The readings for this course are in Gerstner et al., Neuronal Dynamics, sections 1.1, 1.2, and then sections 1.3 up to, but not including, section 1.3.4. If we didn't know what a neuron did, but we wanted to model what they do, we could try and figure out what it does by feeding in different inputs and observing how it behaves. We could reverse engineer the black box that is the neuron. And with enough input-output observations, we should be able to work out what the neuron is doing. So we're going to ask how the outputs of the neuron change as the inputs vary. And we can get this information from experimental methods in biology, where people observe the behavior of neurons. You can start, like Hubel and Wiesel did, observing neurons in organisms that were stimulated by presenting stimuli through the visual system. You can also look at neurons in situ in networks where you directly inject current into the neurons, bypassing the sense organs, but they're still living and operating inside of an animal. And then finally, people have collected observations by stimulating neurons that have been isolated in Petri dishes, again, injecting current directly into the neuron and observing the behavior of that neuron. And the behavior comes out, of course, we can see in terms of the spikes. And here is a plot of rasters of spikes, and we can look at the behavior of populations as well. And we can collect this information and use this to process or try and figure out what the model of the neuron is. So if we're stimulating the neuron with some input, say sensory input or injected current, then we will see that the behavior of the neuron changes. So this as we change the intensity of the stimulus. So this top graph here, or this little figure, shows us the spiking of a neuron, one particular neuron, as it is stimulated by some input. Say light luminance is input going into the sensory system of an animal. And we'll see that as the intensity of that stimulus increases, so too does the firing rate, the number of action potentials per second of the neuron will increase with stimulus. And it will, for smaller changes in the input, it will change less than for larger changes in the input. And so this leads us to propose a theory that this black box here, the neuron model, is computing some nonlinear function of its output, sort of like this sort of curved line here that starts off a little bit slow, accelerates in the middle, and then saturates at the top. And so we can identify that by looking at biological behavior, that there is a threshold, theta here, for which the behavior of the neuron changes. And below this threshold, we won't see really any real changes in the neuron behavior. And above it, the neuron will demonstrate sensitivity to the input. And this threshold is an important part of the nonlinearity. And we will want a neuron model to have a background firing rate that doesn't start increasing until the input crosses the threshold. And this, of course, is another important thing to remember, that neurons do have some background firing rate. So let's attempt to describe this behavior as a nonlinear function to map inputs to outputs in an effort to describe experimental data. That being said, if we want to model this as a typical mathematical function, then we'll prefer to deal with continuous values, and that is not necessarily the case that the data are continuous when we're dealing with experimental data. The output data of a neuron is spikes, which are discrete activities that happen at specific times, but we can turn this into a continuous value by looking at the firing rate, or computing the firing rate, which is the number of spikes that occur per unit of time. The inputs of the function can vary depending on what kind of experimentation we're doing. If we're looking at neurons in an animal, again like Hubel and Wiesel did, then the input is sensory input, and we may be fortunate in that this kind of quantity is already continuous. It could be the intensity of the stimulus or the duration of stimulation as a function of time. And then if it's external current that we're injecting into the neuron, bypassing the synapse, it's just going directly into the neuron, then again the current intensity or the current duration are quantities that we can measure as continuous values that we can put in the neuron model. If we're looking at a neuron situated in a network of other neurons, though, where the inputs are spikes, these quantities are discontinuous. So we'll need to do something about this. And the way to do that is to create a second black box, H, which is the synapse model. And so the synapse model represents how spikes are processed. And then F, the neuron model, models how neurons respond to inputs of different strength. So as we can see, when we're dealing with the nicer data forms, they can be bypass the synapse model and go directly into the neuron model. And then if we're dealing with spike data, we put them into the synapse model that gets translated into the similar kinds of quantities that we can put through the neuron model that become output spikes that then get averaged out to be a firing rate. So a typical approach to modeling H is to turn spikes into current. But what's important to understand is that H is a model for how synapses interpret spikes, and we would like it to have certain properties. It should output some magnitude to reflect the synapse strength /number/size, which is the weight, as we've been dealing with them in artificial neural networks. And then it may also have a time constant that captures the effects of spikes arriving in time. And so it has a filter. And similarly, we also have some requirements we would like to impose on F as well. First is that it should accept whatever the output of H is. They want to be speaking the same language, so to speak. And then the output of F should be something that we can compare to experimental results. And here again, firing rate is a convenient choice. So let's explore this breakdown a little and start with a neuron model that we're already familiar with. Here is an artificial neural network where we have the synapse model H is just a weighted sum of the input spikes that are transformed into a current that is fed to the neuron model F, which is just a step function with a bias, or the threshold, rather, not a bias. And this has this function, which is a nonlinearity. So if the output of H is greater than the threshold, then F outputs a 1, and then it outputs a 0 otherwise. And this is on the simpler end of the spectrum of neuron models. It's purely feed-forward, and it has no temporal integration of spikes. As the spikes come in, the weight gets added, it gets thresholded, and then we get the output. Let's also take a quick look at a more complex model. This is the conductance-based Hodgkin-Huxley model. Here, H and F are components that are more tightly integrated than what we've seen in the basic artificial neural network. The H model here explicitly models the activity of different neurotransmitters like NMDA or GABA. And it directly affects how open the ion channels in the neuron in the neuron body, cell body are. And so F, as a result of the activity of the synapse model, F is injected with current, and it accumulates the current, and that updates the voltage, which then causes the neuron to spike once it's met a threshold, and this produces the action potential. And we're going to come back to this model in a future lecture, but it's important to highlight this at the other end of the spectrum in terms of neuron model complexity or biological fidelity. But for now, let's assume that we have some synapse model H that converts spikes to current and that it transmits to the neuron model F. And here what we want to do is talk about activation functions. These are functions that transform the input current into the firing rate. Examples we've already encountered of these models are the step function, right, this hard step function here, the sigmoid function, which sort of squashes everything between 0 and 1 and transitions smoothly from one to the other, and then the ReLU function, which is 0, output 0 below whenever there's no or negative stimulation, and then outputs whatever the input is once it gets the stimulus crosses the threshold of 0. These are fairly simple neural models, and they're sufficient for most artificial neural network applications. However, they are not necessarily sufficient for modeling biological data. They all have their own individual failings, or not failings, but lack of fidelity to the biology. The step function here has a current output, a constant output, regardless of what the input current is. And this is not biologically plausible. We've also seen that this sigmoid function here it also is lacking biological plausibility because the firing rate is always strictly greater than 0. This is not always the case with neurons. And then finally, the ReLU addresses both of these functions in that sometimes there is a 0 firing rate, and it is not a constant output once it's crossed the input has crossed the threshold. But where this falls down is that the input increases without bound purely as a function of input. And this is not the case. That what we often see in biology is a saturating curve, like we see with the sigmoid function. So if we want to explain the biological data, then we're going to need a fancier function for the neuron model than what we previously encountered. But here we encounter another problem. So it would be easy for us to fit a function to any one neuron that we've collected data for and reproduce the observations. But we'd also like to have a model where we can change some parameters and explain different sets of biological data. In many respects, if we have that kind of a neuron model where we can change a few parameters and fit better biology data, then or fit different sets of biological data, then we might have some confidence or belief or intuition that this model we're constructing tells us something about what the biology is doing. Or at the very least, it would be a useful model. So this is reminiscent of the problems we've seen before, that we want to fit the data, but we want this model to generalize to other data points as well. And then there are some other theoretical problems we have to deal with. The neuron model we're trying to build should behave differently above and below the threshold, and we don't necessarily, even if we want this input to change as a function of time, we don't necessarily want to have time as an explicit variable. So the solution to this is to assume that f is not just a function of input current, right, whatever the output of the synapse model is, but that it's a function of some state variables that change over time, and that those state variables change over time with in part due to influences from the input current. So let's propose our neuron model has the following characteristics. That the input current from the synapse model H updates the state variables, and we will start by saying it does it through addition. that the state variables follow some dynamics, like they want to return to some equilibrium state. So this is elided here in the dot, 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 or the ellipsis. We will come back to these dynamics in a bit. And that the output of the neuron depends on the state variables as well as the transfer function. For example, instead of thresholding the current, we want to threshold on the state variables. Although this then raises the question, what should we use as the state variable? To find the right state variable, we turn to the biology. And what we learn is that the voltage or the membrane potential in the neuron is a likely candidate for the state variable for the following reasons. We want the state to be isolated from the rest of the brain. We want it to be unique to the neuron. And the cell membrane maintains a chemical and electrical gradient between the inside and the outside of the cell. We also want to be able to measure the state. And we can measure the membrane potential of neurons, and we also observe that most cells have a resting potential of approximately minus 65 millivolts. We wanted the state to be dynamic. And we can see, looking at these plots of membrane potential, that there is in fact some dynamics going on, and membrane potential tends to try to return back to the resting potential after perturbation. So we see input here, it returns. Input returns in both cases. We also we want the state to be changeable. That is to say that the voltage is affected by input currents. And we can see that when we have input injections of currents going into the neuron at these from these cells, that the membrane potential changes in response. So here we have, one spike come in, and then the voltage increases. We get another spike coming in from input neuron A. The voltage increases, it crosses the threshold, and we get the nonlinearity, which brings us to the next point, is that we wanted the state to be we wanted the neuron model to be a nonlinear function of state. And we see that exactly here, that when this current is coming in, it's increasing, and then we get the threshold. The spike is a result of the thresholded voltage or membrane potential. And so this concept of membrane potential then fits the criteria we had for the state variable in the neuron model that we're trying to design. So in the next video, we're going to discuss a number of different neuron models that have state. And then we will clue up with a preview of a more complex neuron model that we'll cover in the next lecture. Thank you.